Good evening, everyone. Today we will complete the last lecture. Let's complete the most information about the Zener diode. We will try to solve some examples to can apply the important equation, the current equation equal the power divided on Zener voltage. Let's start from this example. We have this electric circuit. Now we're dealing with independent voltage source and the current direction from this side, from a plus to negative. And here we're dealing with resistance has 1 kilo ohm, that's mean 1000 ohm. After that, we're dealing with Zener diode, cathode anode. Here, it's reverse bias because the plus terminal connected with cathode Zener diode. Let's keep going. At reverse bias, like I said before, we have important condition. We must be careful when we're dealing with it because without apply this condition, we can't calculate any current or voltage from the Zener diode. Here, the voltage source 14 volt bigger than the Zener volt because here 12 volts. Now to calculate the reverse volt at the ohm at this resistance, sorry, we will use the V total equal the V source plus the Zener voltage. All that to calculate the voltage at the resistance. Like we're seeing here, we must calculate the voltage at this resistance and the current at this resistance. Let's keep going. Now the voltage at the resistance 1 kilo ohm equal to volt. After that, to calculate the current, reverse current at the circuit, we must use Ohm law. Voltage equal current dot the resistance, because that we can calculate the current at this resistance equal the reverse voltage or breakdown voltage divided on the resistance. Resistance, like I said, 1 kilo ohm, that means 1000 ohm. 2 volt divided on 1000 ohm equal 2 dot exponential minus 3 ampere or 2 milliampere. Let's go to another. Now we're dealing with another independent voltage source equal 50 volt. Ohm that was the same 1000 ohm and the same Zener diode. The reverse bias, the same thing, plus with the negative with the cathode. The condition is applied because here V source bigger than the Zener voltage, because that the current will through from it. We will use the V total to can calculate the voltage at this resistance. V total equal the V source plus the Zener voltage. By that, the voltage at the resistance equal 38 volts from Ohm's law. From Ohm's law we will start to calculate the current on this resistance. The voltage, the reverse voltage at this ohm, or sorry, the voltage at the current, we will calculate it from V total law, and we calculate the current at this resistance by using Ohm law. Ohm law, V equal current dot resistance, IR equal the current at this resistance equal voltage at resistance divided on the resistance. 38 divided 1000 equal 38 milliampere. Here, ampere dot exponential minus 3 be 1 divided on exponential minus 3 be 38 milliampere. Here, now, this example is different from the last two examples because here we're dealing with two resistance. We can say the first one RS, the resistance near from the source, and the next one I named it R sub L. Here we dealing always with Zener diode at reverse bias with the same condition, must be the V source bigger than VZ. Here this condition is applied. 18 volt bigger than this 18 volt, yes, equal bigger than 10 volt. That's mean we dealing with current. Now let's start to calculate the IS and IZ. From Ohm's law, voltage equal current dot resistance. Here, the current at the Zener diode equal the voltage Zener diode, the Zener voltage divided on resistance. Here the resistance is 250 ohm. Here some wrong, I said, I think. Here IZ, yes, with 1000 ohm, and I source with 280 ohms. That's right. Here, let's say we can divide the circuits to two parts. The first one will be this, the circuit between the voltage, the Zener voltage, and with the RL. And the next one will be from the Zener diode on the voltage source. We will start, that's mean from here, from this first circuit, by using Ohm's law to calculate the current, the Zener current, with the RL equal 1000 ohm. Here IZ equal VZ, we know it, 10 volt divided on ohm, 1000 divided on resistance equal 1000 ohm, equal 10 milliampere or 0.01 ampere. Here, let's go to the next circuit to calculate the current at the next circuit between the Zener diode and voltage source. From Ohm's law, here the IS, the current at the second circuit, equal VS, that means the source voltage, here the independent voltage source, equal 18 volt, divided on 250 ohm. But here we don't have the VS, because that we must calculate it by using V total equation. V total equation equal VS plus the source voltage plus the Zener, the voltage at the resistance, plus Zener voltage. We know the voltage source result and the voltage Zener value. By that, we can calculate the voltage at the resistance. The voltage at the resistance, here must write R, not S, equal 8 volt. By that, IS equal the voltage at the resistance divided on the resistance, 250 ohm, equal 0.032 ampere or 32 milliampere. After that, let's calculate the power. Like I said, it was important equation. The current equal the power divided on the voltage, the Zener voltage or breakdown voltage. Here, by using this rule, equal the current equal the power divided on breakdown voltage, we can calculate the power equal current dot Zener voltage. Here we have this result, IS, the current to the circuit, equal 10 milliampere dot the voltage, Zener voltage. We know this result is 10 volt, the result will equal 100 milliwatt or 1 watt. Let's go to this, the last image here, to illustrate the both of them, reverse bias and forward bias, must be able. We can connect all of them by using the same bias kinds at the same circuit. We can know the which of them will be reverse bias and the other which of them will be forward bias from the current direction. Here the current direction will select to us, for example, here it's reverse bias, but here it's forward bias, plus the positivity terminal with the positivity terminal to anode to Zener diode, and after that come back to negativity terminal source. Let's do some simple similarity to these two lectures. The Zener diode can use, like I said many times, a regulator voltage to protection our devices in the electric circuits like regulator. The most feature in this, and this feature make me very interesting to this topic more, let a current through from two direction, like forward bias and reverse bias. And this diagram is very important to us because explain to us the moving between these two wave, the positivity wave and negativity wave, but here with a different shape, because here at first the positivity side is more than the negativity side. Or actually we can say here we don't have negativity side, because this clumped output be near from 0, and after that suddenly increasing again. When we apply a voltage more than zero voltage, the bottom of the sine wave get clipped off like this, and the top will be swinging like that, completely normal and swinging. Different from the bottom is be like clumped out, and all them results will be near from 0 at the x-axis, positivity x-axis. Here the top output is swinging like I said before, and we can say start from minus dot 8 volts. That's mean near from 0. That means we will dealing with some negatively results, but all of them will be near from 0. 2 plus 2.6 volt, like I said before, the positively wave will be more than the negatively wave, or we can say near from 0. That's it. Thank you for watching, for patient. I will see you in another video to discuss together another important and interesting thing. Let me stop the recording, and that's it. Görüşürüz. Kendinize çok iyi bakın.